So today we're going to redo the video for our simulating an RC in several different ways because the sound didn't work, and I do apologize. I'm just going back here. I'm seeing the sound button, so I think we're good to go. Sorry about that. So what we have here is an RC circuit, but usually in books they start off with the capacitor here and the resistor here. And this turns out to actually be a high-pass filter. And we can think of it in this way, is that this impedance and this impedance make a voltage division, that this impedance gets smaller with frequency, and so ultimately as the frequency goes up, the voltage at 2 gets very, very close to the voltage at 1 as frequency goes up. So the first thing we're going to do is a DC simulation. Now it's not too exciting because we can put 1 volt source here, but this capacitor is an open at DC, so no current will flow, and so this node here should be at 0. We need to run it, and the way we run a DC simulation is putting a .opt. And out pops V2 of 1 times 10 to the minus 15 volts and a very small current. Although we'll get to the negative sign later. So that shows what happens at DC. Now let's see what happens for a transient. Now you can put in a sine wave for a transient. For instance, we can have an offset of 0, an amplitude of 1, frequency of a kilohertz. All right, 1 kilohertz sine wave. I can change the simulation command to transient. We'll keep it at 10. All right. We can notice now it's .tran 10 milli, and the OPT is now commented out with a semicolon. So now we run it, and in order to see the waveforms, I have to click on them. All right, and what we see is that after some initial startup, that V out is almost equal to V in, but that there is a time delay. All right, but this sine wave this is time, and this is a 1 kilohertz sine wave. Now when we do AC simulations or Bode plots, what we do is kind of send a sine wave at various frequencies and just take the relationship between the amplitudes of the two waveforms, input and output. Now one of the biggest things to do for a transient response is a pulse. So we can start off at 0, go to 1, and we will delay 1 millisecond. Now we can, 1 nanosecond rise and fall times will approximate a step function of infinite slope. We can stay on for 5 milli because that'll be 5 tau, and our period can be 10 milli, which should show all the data we want. Now it does get messy in here. If I click on F8, I should be able to stretch that out. That's okay if it didn't work. I'll just add another line. Now I can run this again. All right, and we'll talk about that later. Don't really want to see it, but I'm going to just go to 6 milli because this really starts, the step happens at 1, and the way I can see that more clearly is setting the tick so that you can see that a lot more easily. So we have a pulse, goes from 0 to 1, looks almost infinite, slope at 1 millisecond, and then, 5 tau later, I am discharged to more than 99% of where we started. Now, that's 5 tau. Now, just because some people might look from, oh, 0 to 6, 5 tau is 6 milliseconds. It's not really. Remember, we started off here at 1, all right, and went to 6. And sometimes I can even stretch this out to 6. I can simulate for 7, and not to get tricked, but just because I'm out here at 7 doesn't mean that that's 5 tau. You take, in this case, it's just e to the minus 5. You find that point. It happens to be at 6, and that would be 5 tau. All right. But yeah, on an exam, it can be a little bit hard to read exactly where 5 tau is, but you just have to be pretty close. All right. Now, the next thing we're going to do is a AC analysis. And in order to do that, what we do is we set up an AC amplitude here of 1 and a phase of 0. And what that's saying is, hey, we're going to have a sine wave with an amplitude of 1 and a phase of 0, but we're going to change the frequency. And then we're going to automatically calculate the amplitudes. Now again, this won't change it because I've still got the transient there. So we have to come back, edit the simulation command, AC or Bode plot, or maybe you could even call it S domain. I want to do a sweep of frequency by decade. I want 20 frequencies per decade. I want to start off at a hertz and end up at 1 megahertz. Okay. And now that's the active analysis, and that one is commented out. So now all we have to do is run, and we see not a step response of a low-pass filter, because notice this scales in dB, and this is in frequency, not time. But see, V1 at every frequency is at 0 dB, which 20 times the natural base 10 log of 1 is 0 dB. And we can see that V2 is attenuated quite a bit near DC. 1 hertz is still 1 times a second, but that's getting pretty close to a DC signal. Now, what's the point of interest? Well, over here, it should be 0 dB, and negative 2.59 micro dB is pretty darn close to 0. Now I can brag this out and try to find where it says minus 3. All right. And that's pretty good. So that's minus 3 dB. That point is the cutoff frequency, and as you've seen in the notes, that's 1 divided by 2 divided by pi divided by tau, which in this case is 1 millisecond. Well, when you calculate that out, it should be 159 hertz. And lo and behold, it's at 159 hertz. Now, some people get a little confused because this kind of looks like the step response of the low-pass filter, and they might think, oh, from here to here is 5 tau. No. Remember, this is frequency, and that scale is dB, and this 1 point gives us 1 over 2 divided by pi divided by tau. But something to notice is that the larger tau is, right, the more it should block the lower frequencies. So if I change this to 10, right, 10U, tau just increased by a factor of 10, and now tau changed to, or the cutoff frequency changed to about 150, 15.6. Okay. And so by changing tau, the larger tau, the more the cutoff frequency heads in this direction. All right. So just to recap, right, this point is the cutoff frequency and is related to the inverse of tau. But in a transient, oh, let's get rid of this just in case. Oh, that's right, I changed tau. All right. 5 tau is when you get e to the minus 5 of where you were, which is here at 6 milliseconds. Since we started at 1, 5 tau is 5 milliseconds. And that's it.